In this lecture, we are going to see independent random variables and then the concepts of covariance and correlation. So, what is independent random variable? So, the random variables x1, x2, xn are said to be independent if the joint cumulative distribution function of x1, x2, xn can be expressed as the product of the marginal cumulative distribution function of each xi. Okay, so I have n random variables. So if the marginal, joint cumulative distribution function of x1, x2, xn can be written as the product of the marginal cumulative distribution function of x1, x2, xn, for each x1, x2, xn in Rn, we say that the random variable x1, x2, xn are independent. Notice that this relationship, this equality has to be true for all x1, x2, xn in Rn. So for all point in Rn, this relationship has to be true. If this relationship is true for some points in Rn but not true for other points in Rn, then x1, x2, xn are not independent. x1, x2, xn are only independent if this equality holds for all x1, x2, xn in R to the power n. Okay, fine. So next what we are going to see is that two equivalent definition for discrete random vector and continuous random vector. Okay, and though we are not going to give the proof of this thing, but these alternative definitions are very handy in many practical scenarios. So for discrete random variable, what is discrete random vector? What is the equivalent definition? Let x1, x2, xn be a discrete random vector with joint probability density mass function small f x1, x2, xn. Then x1, x2, xn are said to be independent if the joint probability mass function can be written as the product of the marginal probability mass function for all x1, x2, xn in R to the power n. Again, notice that this equality has to be true for all x1, x2, xn in R to the power n. Okay, so if the joint PMF can be written as the product of the marginal PMFs, then we say that x1, x2, xn are independent. Okay, clear? This is for the discrete one. And now you can understand what is the natural extension for the continuous random vector if the joint PDF can be written as the marginal PDF. Again, notice that it has to be true for all x1, x2, xn. So in the three definition, the equality has to be true for all points in Rn. For all points in Rn. Okay. So the first definition, which is given in terms of the cumulative distribution function, this is the most general one because cumulative distribution function exists for all kind of random variables. So this is the most general definition. But for the discrete random vector and for the continuous random vector, the equivalent definition can be given using the joint PMF and marginal PMF and joint PDF and marginal PDF respectively. Okay, fine. So I hope the definition is okay with everyone. So one of the very plus point of the independence. So independence intuitively means that the one random variable does not have any effect on the other random, just like the independence of events. And in fact you can see that you can see from this definition, if you have two random variables x and y, then the independence, the definition of the independence is basically for two random variables x and y are independent if the distribution function of xy at the point xy can be written as distribution function of x at the point x into distribution function of y at the point of y for all xy belongs to R square, right? That is from the definition. Now you notice that what is this thing? This thing is basically probability that x is less than or equals to x, y is less than or equals to y. And this side is probability that x is less than or equals to x, into probability that y is less than equals to y. And again, this has to be true for all x, y in R square. Right? Clear? So that basically means that x and y are independent if and only if the event x equals to x is less than equals to x, x is less than equals to x, and the fy, which is y is less than equals to y, if it event this and this are independent for all x, y belongs to R square, right? So the two random variables x and y are independent if 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 x is less than equals to x and y is less than equals to y. These two events are independent for all possible values of x and y. Okay, clear? So now, so that basically means that the concept of the independence actually come from independence of two random variables actually come from the concept of the independence of two events. But in this case, instead of the two events, this event ex and efy has to be independent for all possible values of xy in R square. Okay, clear? So now let us see the next theorem, which is basically regarding the expectation. If two random variable x and y are independent, the expectation of g of x multiplied by h of y can be written as expectation of g of x multiplied by expectation of g of y. So independent expectation of the product can be written as the product of the expectation. Okay, but for that I need the independence condition. So independence of two random variable implies that expectation of the product can be written as the product of the expectation. Obviously I need that all the expectation, this expectation as well as these two expectation, these three expectation has to exist. Okay, the proof is very simple. I write the proof here for the continuous random variable, but for the discrete one, you need to just replace this in the integration, double integration with double function. That's the change you need to do. So how it goes for the continuous random vector? So if xy are continuous, that means this is a density function. So this expectation is nothing but this integration. Okay. Now, because x and y are independent, that means the density function can be written as the product of the marginal density function. Now, once you write this way, the x only involves in g and this part, and y only involves in h and this part. So you can easily separate them out into two integrations, and each of the integrations are basically two expressions. So the proof is very simple. Once you use the equivalent definition here, that the joint density function can be written as the product of the marginal density function. Clear? So in case of the independence, this is one very helpful thing, that the product of the expectation of the product can be written as the product of the expectation. Okay. Now let us see two new quantities, two new measurements. One is called covariance, another is called correlation coefficient. So firstly, what is the definition of the covariance and what is the definition of the correlation coefficient? Then I will come to the physical meaning of these two quantities. So what is covariance? The covariance of two random variable x and y is defined by expectation of x minus expectation of x multiplied by y minus expectation of y, and then outside you have expectation. And this quantity you can write in this manner also. Just take the product and use the linearity property of expectation. You will find that this product can be written in this form. Okay. So covariance is basically nothing but expectation of x minus expectation of x into y minus expectation of y, which can be written as expectation of xy minus expectation of x into expectation of y. Okay. And correlation coefficient is nothing but the covariance divided by root over variance of x into variance of y. Okay, fine. Now come to the physical meaning of the covariance and correlation. So the physical meaning of covariance Okay. So physical meaning of the covariance can be explained in the following manner. Suppose you have a data. Okay. Suppose you have a data, and you have a data on two random variable x and y. When you plot the data, suppose it look like something like this. Okay, it is clustered something like this. For another data, suppose the clustering is in somewhat in the other direction, suppose in this manner. Okay, clear? And the other one, suppose the clustering is something like this. Okay, clear? Now, you see that the covariance, so think about these three data sets. Now you see that the covariance as we have defined is expectation of x minus expectation of x into y minus expectation of y. Okay. Now the expectation of x is basically nothing but the mean of x, and expectation of y is mean of y. So the expectation, so the point expectation of x and expectation of y will be something in the middle. Okay. This point is basically point expectation of x, comma expectation of y. Similarly, in this case also, this is sometime in middle, this is something in middle. Now, if you consider the point, now if you consider the point x minus expectation of x, comma y minus expectation of y. Consider this pair of points. What is this? This is basically nothing but as if I have shifted my origin, as if I have shifted my origin to this point. Okay? So the origins are now shifted here. Similarly, in this case, origin are shifted here. In this case also, origins are shifted. Okay, clear? Now, if you consider this point again, note that both the component in this point will be positive in this part, both the component will be negative in this part, and one of them is positive here, another is negative here, the similar thing is there also. So the component of this point, component of this kind of points are sign of the components are opposite in these two parts, whereas the sign are same in these two parts. Now, when I consider the product will have a positive sign here, product will have a positive sign here, product will have positive sign here, and the product will have negative sign here, negative sign here. So, in this particular scenario, you see that the most of the products will have the positive sign, less number of products will have the negative sign. Similar, the scenario is opposite here. In this case, most of the point have negative product and less number of point has positive product. And in this case, the negative and positive are almost of the equal number. Okay, negative products and positive products are almost in the equal number in the last. Now, what is this expectation? This expectation is nothing but the average of the product, right? So if you have a lot of positive signs and less number of negative signs, so it is more likely that the average is also positive. So if you have the data orientation in this manner, then the sign of the covariance will be positive. But if you have the data of this manner, the sign of the covariance will be negative. And in this case, the sign of the covariance, or rather value of the covariance, will be very close to zero. Sign could be positive, could be negative, but the value will be close to zero. Okay, clear? So that means, see, in this case, what is happening? On an average, when x increases, y also increases. In this case, when x increases, y decreases. And in this case, there is no such kind of relationship. And you see that covariance, the sign of the covariance actually capturing it. when we have a positive relationship, positive in the sense when one increases, another also increases on average, then you have a positive sign of the covariance. When you have a negative relationship in the sense that one increases, another decreases, you have a negative sign of the covariance. When there is no such strong relationship, covariance sign could be positive or negative, but the value will be close to 0. Okay, so I hope the physical meaning of covariance is clear, and the physical meaning of the covariance is that it explores what kind of relationship between two random variables has, whether they are increasing on an average or whether one increases implies a decreasing of the other on an average, or whether there is no such relationship. If the sign of the covariance is positive, that means that when one increases, another also increases on an average. If the sign of the covariance is negative, it means that one decreases implies that other increases on an average, and when the value is close to 0, that basically means that there is no such strong relationship. Okay, this is basically the physical meaning of the covariance. Now, because covariance is defined like this, it is the expectation of some product. You see that this expectation in general could be any value. It can lie from minus infinity to plus infinity. It can take any value between minus infinity to plus, right? So minus infinity is less than covariance between xy is less than plus infinity. I am assuming this covariance exists, so that's why basically the equality signs I am not including here, but covariance can take any value in the whole real life, because it's a simple expectation, so it is an integration or multiple integration, so it can take any value in the real life. So now there is a problem. The problem is basically, if I want to say that the relationship is strong or relationship is weak, I cannot tell based on the, relationship is weak, I can tell sometimes based on the value of the covariance. If the value is close to 0, whether positive or negative, I can tell that the relationship is weak. But when I tell that relationship is strong, how strong? I cannot tell based on the value of the expectation, because it is an unbounded quantity. Okay? Not unbounded, basically I wanted to say that it can take any value. So a 5 value, suppose I got the covariance of two random variable x and y is 5. But how strong that 5 means, how strong the relationship this 5 means, that I cannot tell, because it can take any value between minus infinity to plus infinity. Okay? So, but if I have some quantity which has two finite bounds, which always lies between two finite values, I can tell that it is a strong one, whether it is a strong one or whether it is a weak one. And this correlation actually do this one. The correlation, in case of the correlation, what we did, the covariance is scaled using the root over variances, and that actually do this one. We will show within few minutes that correlation always lies between -1 and +1. So if that means basically a value close to -1 or close to +1 tells me that the relationship between x and y is quite strong. If the value is close to 1, that means that the relationship between x and y is positive and the relationship is quite strong. On the other hand, if the covariance is close to -1, I can tell that the between x and y there is a strong negative association. Okay, yeah. So that is basically the one way of improvement over the covariance. So correlation coefficient is one way of improvement over the covariance. Another plus point in correlation coefficient is that this quantity is unit independent. Even if you have some unit of the random variable x and y, you see that because of this product, the unit of the covariance will be the product of the unit, and because of again product in the denominator, the variance of the unit is variance. The unit of the variance is the square of the unit. Okay, so when you take the root, it comes out and it cancels. So basically, this correlation coefficient is a unit-free quantity, and that's why that coefficient term is used here. Okay, clear? So I hope that the physical meaning of the correlation coefficient and covariance are clear to everyone. Okay. Now let us see the remark 3.6. So as I already mentioned, that correlation or covariance actually measures some association between two random variables. Okay. Now, if x and y are two independent random variables, that means they do not have any association. So in this case, covariance should be zero. And it can be shown that actually covariance is zero if x and y are independent. How? Okay. The covariance by definition is nothing but expectation of xy minus expectation of x into expectation of y. Now, because x and y are independent, I can use this theorem and I can write that expectation of x into expectation of y, expectation of xy as expectation of x into expectation of y. So these two terms cancels out and I got that covariance is zero. And this shows that if x and y are independent, then correlation coefficient is also zero provided the variance exists. Okay, fine. Now, natural question comes into the mind, is the converse true? That means covariance zero, does it imply that x and y are independent? Right? So, and the answer to this one is not true always. And with the example we show it here. So, suppose your x has a normal random variable, a normal 0, 1 random variable, and you take y equals to x square. What is the covariance between x and y? The covariance between x and y can be written as covariance between x into y into covariance of x into covariance of y. Because y equals to x square, just plug it in here, I get that expectation of x cube minus expectation of x into expectation of x square. What is the expectation of x cube? Because of the x follows normal 0, 1, you can easily show that expectation of x cube equals to 0. I am not doing it, it's a very simple one to check. Just write down the integration, you will find out that expectation is 0. So expectation of x is 0, expectation of x cube is 0. That implies that this quantity is 0, this part is 0, so covariance is also 0. So covariance between x and x square is 0. Now, are they independent? Intuition says they should not be independent. Let us check whether they are independent or not. So how can I check this one? Again, remember the definition of the independent. So two random variables are independent if f of xy is equals to f of x into f of y for all xy belongs to R square. Now, if I can show that this equality is not true for at least one pair of xy belongs to R square, I can tell that x and y are not independent. Yes? If I can now show that for at least one pair xy, this equality does not hold, I can tell that x and y are independent. Exactly that's what I am going to do now. So, I start with probability that x is less than or equals to minus 5, which is basically the which is basically the cumulative distribution function at the point minus 5, and which is not equals to 0 because x follows a normal, x follows normal 0, 1, so that means this probability is not equals to 0. On the other hand, if you take y is less than equals to 1, which is basically probability that minus 1 is less than equals to x is less than equals to 1. This is because y is equals to x square, that means x square is less than equals to 1, basically means that x lies between minus 1 to plus 1, and which is basically capital phi at the point 1 minus capital phi at the point minus 1, which is again not equals to 0. Okay? Now, think about, so this is basically the distribution function of x at the point minus 5. This is the distribution function of y at the point 1. Now think about the joint distribution function of xy at the point minus 5 and 1, which is probability that x is less than equals to minus 5 and y is less than equals to 1, which is basically probability that x is less than equals to minus 5 and minus 1 is less than equals to x is less than equals to 1, which cannot happen, so this probability is 0. So that means that this joint probability cumulative distribution function at the point minus 5, 1 is not equals to distribution function at the point minus 5 multiplied by distribution function at the point 1. So clearly the random variable x and y are dependent random variables. Okay, clear? So we have seen that though the covariance is 0 in this case, but the random variable are dependent. So that means that if you have independent random variable, covariance is 0, but covariance 0 does not imply the random variables are independent. Yes? If this thing is mine, I have seen that many students make mistake in this one. Many times they write that covariance 0 implies they are independent, but this is not true. Okay. Now, okay. Now there is a theorem which basically talk about computation part of covariance and variances. So the first point says that covariance between x is equals to variance of x. It is very easy to see from the definition of the covariance. The next one says that covariance between x and y is same as covariance between y and x. That is again straightforward from the definition of the covariance. Third one, covariance between ax and y is same as covariance a times covariance of x comma y. So the constant come out of the covariance. And then it is again very simple from the definition, because covariance between ax and y by definition is this one. Now you can take this a out of the expectation because a is constant. So that's why I get this quantity same as a times covariance between x and y. Okay, fine. So then the fourth one, which says that covariance between x plus z and y is same as covariance between x and z and covariance between z and y. It is again very easy to see from the definition. It is nothing but kind of a product rule, that x and y then z and y. Okay, it is a kind of a product rule, and the extension of this one is basically 5 for a more than 3 random variables. I have n random variables there, m random variables there, I have some constants. Again that product rule works, that sum come out, constant come out, and then I have covariance between xi, xj. Okay, now you can see this 6 basically come from combining 1 and 5. And they said that variance of summation of random variable can be written as summation of variances plus 2 times summation of covariances. Notice that here I have I is less than j. Notice that here I is less than j. If you write I not equals to j, then these 2 will not be there. And finally, if your xi's are independent, then this covariance term will be 0. That's why for independent xi's, variance of summation of xi is same as summation of variances. So if you have independent random variables, then variance of summation is same as the summation of variances. Okay, so the proof are simple, but just write it down once and cross-check all the proofs. I am just leaving it for you. The next theorem, which is basically I have already pointed out, that correlation lies between -1 and +1. Why? So the proof is quite simple. So suppose you take lambda belongs to R and consider the random variable x plus lambda y. So x plus lambda y is a random variable, because x is a random variable, y is a random variable, z is some quantity in R. And we know that the variance is always greater than equals to 0. So the variance of this random variable is also greater than equals to 0. Now break the variance. Break the variance using this formula. Using this formula, here n equals to 2, and when you break this one, you get this basically nothing but variance of x plus variance of lambda y plus 2 times covariance of x and lambda y. Now this variance of lambda y can be written as lambda square times variance of y. Covariance of x comma lambda y can be written as lambda times covariance of x comma y, and then I have variance of x. Now, so that means basically this quantity is always greater than or equals to 0. And what is this? This quantity is nothing but a quadratic form in lambda square. So that means that this equation either has no solution or exactly one solution. Because this quantity is always greater than equals to 0, that means this equation either has this quadratic equation in lambda, either has one solution or has no solution. What does this mean? That means basically discriminant is either negative or equals to 0. And what is the discriminant in this case? Discriminant is 4 times covariance square minus 4 into covariance of y, variance of y into variance of x. So I get this quantity. Now 4 cancels out. You take this variance x into variance y on the other side, divide it. You get that rho square is less than equals to 1, which basically say that rho lies between -1 to +1. Okay, so rho always lies between -1 to +1, as I have already pointed out earlier, and that is one of the benefits of using the correlation coefficient over covariance, as I have already pointed out. I stop here for this lecture. Thank you for listening.